Hi, my name is Faye Jackson and I'm a data analyst in the Environment Group of the Salmon and Freshwater Fisheries Programme of Marine Scotland Science. I've been asked to give a virtual presentation for the University of Birmingham's World Water Day celebrations, and I'm going to be talking to you about river temperature, climate change, and how we can use riparian tree planting as a management strategy. So why are we interested in river temperature? Well, river temperature is really important for the health of cold water adapted fish like Atlantic salmon and brown trout. It influences all areas of their life cycle, from their spawning location and timing, their feeding and growth, their size at age, the size and age when they smolt, and at extreme temperatures it affects their survival. So Atlantic salmon exhibit thermal stress at 23 degrees C and mortality at around 33 degrees C, and brown trout exhibit mortality at 30 degrees C. As a result, there are concerns about how rising river temperatures under climate change will influence fish populations. Many of you will remember the summer of 2018, a hot, dry summer, and recent UK CPAT and climate change projections suggest that summers as hot and dry as 2018 could become as common as every other year by 2050. So what does this mean for river temperature, and what does this mean for our fish populations, and how can we begin to manage and mitigate this risk? Well, riparian tree planting offers one of very few management options for river temperature. We know that riparian woodland can reduce high temperature extremes by shading the rivers and reducing the amount of incoming shortwave radiation. But we know that this effect size is highly variable between locations and between years, and that in order to make large scale strategically targeted efforts, we first need information on, well, where are our rivers hottest? Where are they most sensitive to the effects of climate change? So where are they going to change the most? And where is riparian tree planting going to give us the biggest effect? Where will we see the biggest reductions in river temperature by planting trees? And we need this information to be translated into management and tools and advice that can be used to inform these decision-making processes. So this context feeds into more than 15 years of research by the Environment Group at Marine Scotland Science. Today I'm going to be talking to you largely about our large-scale spatial models and making predictions of river temperature at big spatial scales. I'm going to touch on fine-scale process-based understanding, and I'm then going to talk about, well, how do we translate this research into management and mitigation advice? All of our work is embedded within a calibration and quality control procedure, and if you're interested in that, you can go to our web pages and look at our standard operating procedures and our calibration processes. So how do we use spatiotemporal statistical models to make predictions of river temperature at large spatial scales, both under current and future climate? Well, in the first instance, we need quality controlled river temperature data, and that's where the Scotland River Temperature Monitoring Network comes in. Before 2014, there was very limited quality controlled river temperature data available in Scotland, and even less when you consider locations that were absent of any significant land use change, such as tree planting or tree felling. So what we did was we strategically designed the Scotland River Temperature Monitoring Network to cover the environmental range of characteristics that have been shown in the literature to influence river temperature. And you can consider these to be proxies for processes. So characteristics that we can generate in a GIS at big spatial scales. And what the objectives of the Scotland River Temperature Monitoring Network were was to let us characterise river temperature across Scotland, to identify areas that would be susceptible to the effect of climate change, to improve our understanding of the controls on river temperature, to let us make large-scale predictions of river temperature and predictions of river temperature change, and to then determine all optimal areas for tree planting. The Scotland River Temperature Monitoring Network has more than 200 sites across 13 catchments, and we do have some short-term deployments going in the Forth and in the Naver and Hallidale catchments. The Scotland River Temperature Monitoring Network is a really great example of a successful collaboration between government, local fisheries and rivers trusts and boards, and academic partners through the University of Birmingham, and landowners and stakeholders. We in Marine Scotland Science are involved in all aspects of the Scotland River Temperature Monitoring Network, from logger calibration, data quality control, analysis and publication. Local trusts and boards do the majority of the data logger download and data logger return. And we then quality control the data and analyse and publish the results, often in collaboration with colleagues at the University of Birmingham. We then translate these publications into decision support tools that we can then feed back to local fisheries trusts and boards to help them make decisions on where to plant riparian trees. So when we began thinking about these types of statistical models that were available to us to make predictions of river temperature, there were several technical challenges that we needed to first consider, and these technical challenges informed the final choice of modelling approach. So we know that river temperature is often used as an indicator of the net energy availability, and that this can predict both spatial and temporal variability in river temperature. We know that we see strong site-specific air temperature water temperature relationships, and that these can predict temporal variation in river temperature, but that these relationships vary depending on seasonal changes in discharge, and also vary spatially depending on the influence of different landscape characteristics like the presence of woodland or topographic shading. We also know that river temperature data exhibits substantial spatial structure or covariance, both within river networks and between catchments or regions. And we know that daily river temperature is autocorrelated in time. So many studies have previously favoured using summary metrics like a summer maximum temperature. So if you sum these challenges together, you get an overall modelling challenge of wanting to be able to predict both spatial and temporal variability in river temperature, using air temperature, which is moderated by relevant landscape characteristics, whilst also accounting for temporal and spatial correlation at multiple scales. So you can think of this conceptually using a simple air temperature water temperature relationship. So what you're looking at here is we have air temperature on our x-axis, water temperature on our y-axis. Our colours are different months of the year. The solid lines are the first half of the year and the dashed lines are the second half of the year. And what you can see is that we have a slope and an intercept that varies depending on the time of year, that can also be modified by environmental covariates. So if we take the example of winter, we can see that we have a lower temperature, so a lower intercept, and that our slope is much shallower. So for a given change in air temperature, we have a smaller change in water temperature. In contrast, in summer, our absolute temperatures, our intercept, are much higher, is much warmer, and our slope is much steeper. So for a given change in air temperature, we see a greater change in water temperature. So then to let us make predictions to unmonitored locations, we also need covariates within our model, so these proxies for processes that I talked about earlier, that we can generate for all rivers in Scotland. We're fortunate in the UK that we have gridded daily air temperature datasets provided by the UK Met Office at 5 km resolution through UKCP09 at the time. We were also able to generate landscape covariates like elevation, upstream catchment area, amounts of woodland on the banks of rivers from large-scale GIS datasets. We also used a hydrometric area smoother to describe spatial variability of neighbouring hydrometric areas, so catchments or groups of catchments, letting catchments that are more similar to each other, closer to each other, be more similar than those that are further away from each other. And we did that using Gaussian Markov random fields. Within our catchments, we can describe any residual spatially structured variability in temperature that's not explained by any of the landscape covariates by using a river network smoother. And we can then have random site-to-site variability with random effects. We fitted these models using generalized additive mixed models using BAM from the MGCV-R package. We had a starting model of river temperature as a function of air temperature plus all of the landscape characteristics and day of the year. We then embarked on forwards and backwise stepwise model selection. At each stage, our main effects could switch between being absent from the model and linear, and being linear or smooth. And all landscape covariates were given the opportunity to interact with air temperature. And if a covariate was to interact with air temperature, that allows the covariate to affect both the slope and the intercept of the air temperature water temperature relationship. And we ranked all the models based on Bayesian information criterion. It's a more stringent criterion which tends to result in simpler models that are more transferable. And the result of this process was our national river temperature model for Scotland that we published in Science of the Total Environment. Rather than reading out this equation to you, what I'm going to do is I'm going to talk you through this model and illustrate the model and the process reasoning behind each of the covariates that are included within the model. So I'm going to show you a series of partial effects plots. And what partial effects plots are is with everything in the model held at a median value other than the covariate of interest. And that lets you explore the effects of those individual covariates. In circumstances where you're seeing a 3D plot, this means that the covariate is interacting with air temperature, so it's affecting both the slope and the intercept of our air temperature-water temperature relationship. In all of our 3D plots, we will have air temperature on the z-axis, water temperature on our y-axis, and the covariate on our x-axis. So this example is we're seeing the effects of air temperature interacting with day of the year. And what this is showing us is that we have a steeper relationship between in summer in comparison to winter, which is as you would expect. In summer we have lower flows, the river temperature is more responsive. You can imagine that if you're taking a kettle and you're boiling enough water for 1 cup of tea versus a kettle for 6 cups of teas, it'll take much longer to boil for the 6 cups of tea. We then have effective elevation interacting with air temperature. So again, we have air temperature on our z-axis, elevation on our x-axis, and river temperature on our y-axis. And what we can see is that we have further reductions in river temperature at low air temperatures. And we think that this illustrates the effects of snow cover and snow melt. And you can see that this effect in summer is negligible. From a management point of view, it was then really great to see the effects of woodland coming out within these models. And it's as you would expect, we see at high air temperatures, we're seeing greater reduction in river temperature under higher riparian woodland percentages. And this is illustrating the effects of shading. And again, as you would expect, at low air temperatures, we're seeing slightly higher river temperatures in situations where we have high riparian woodland. And this is the reduction in net radiative losses that we see from riparian trees. So you can imagine the trees acting as a blanket on the river and reducing the amount of energy and heat that's being lost overnight. We then have a very small effect on orientation. So you'll notice that this is a 2D plot. So this means it's only affecting the intercept. And this means that we get slight increases in river temperature in north-south reaches, so our most exposed reaches when the sun is high in the sky. We then have our large-scale hydrometric area effect that shows some large-scale variability in river temperature with slightly warmer temperatures in our northern rivers. We then have within catchment spatial variability not explained by our covariates, is explained by our river network smoothers. And what you can then do with these models is you can make predictions on any day of the year for any river in Scotland. So what we did is we made predictions of daily maximum river temperature under extreme air temperature conditions. So we used air temperature data from 2003. This is comparable to what we observed in 2018, but we did the analysis before 2018. And what this shows is that we have spatial patterns in river temperature that reflect spatial variability in air temperature, characteristics of our rivers, and these regional responses. Our warmest rivers are typically in low altitude locations with high air temperatures that are unshaded, and particularly in the north. What we can then do is we can also look at climate sensitivity. So where do we think is going to change the most? So for a given change in air temperature, so a 1 degree change in air temperature, how much will our river temperature change? And again, we used air temperature data from 2003 to get a more extreme example. And what this shows is that we had biggest changes expected in our northern rivers and in rivers in the Cairngorms. Take these predictions and make these layers available in online mapping environments, either through our National Marine Planning Interface, which is an online GIS environment, or as WMS layers, which would allow you to bring the maps into your own GIS environment. And you can use these outputs to describe our large-scale variability in river temperature and climate sensitivity, and this can inform resource allocation in terms of where you might want to plant riparian trees. But how do we go from making a relatively large-scale decision on where to plant trees to deciding when you're stood on the banks of a river where you're going to plant trees? Well, this is how we can use the results of process-based models which let us understand how riparian shading affects river temperature. There's a wide variety of river temperature models that you can use, and we recently undertook a review with Steve Dugdale at the University of Nottingham on the different types of river temperature models that are available to us. And you can consider a process-based river temperature model as a virtual experiment. You can alter all of your complex energy and heat exchange processes to understand how these processes are controlling river temperature and what might be the effects of different management options, so say removing trees or adding trees. Some previous work that we did with Grace Garner at the University of Birmingham looked at these different scenarios for, well, what are the effects of vegetation density, our channel orientation, and how quickly the water is flowing through our river reach, and how does that affect the effects of riparian woodland on river temperature. And we can take these complex modelling approaches and distill them down into some relatively simple advice for planting trees on the banks of rivers. So you can identify your general locations from these large-scale spatial models, and then use this advice to make decisions on the ground on the banks of your rivers. So things like if you've got a southerly bank available, then you're going to need less tree cover than if you don't have a southerly bank, where you'll need a higher density of overhanging trees. And we know that planting has a greater effect where the rivers are flowing more slowly, where you have more time to reduce the amount of energy that's being added to that river. And we've translated this into a where to plant trees topic sheet that can be used to support this decision-making process. So if you were wanting to decide, well, where can I plant trees on the banks of rivers to manage thermal regime, how would you go about that process? Well, first of all, you would decide, well, what is your planting objective? Are you wanting to protect rivers that are hottest, rivers that will change the most, or both? And that informs which of the prioritization layers you would use on NMPI or the web-based mapping service. You would use this to identify catchments or kilometers of rivers that you may wish to plant trees on. You would then combine these locations with our planting potential advice from the Where to Plant Trees leaflet that will let you decide within that kilometre where are you going to get the biggest benefits from planting trees. And I asked at the start, well, is summer 2018 an indication of things to come? So one of the most recent pieces of analysis we did was making predictions on every day of summer 2018 for all rivers in Scotland. And what this analysis showed was that 69% of our rivers experienced one or more days of river temperature greater than 23 degrees C. And we've made this available in our summer 2018 river temperatures leaflet, which you can find online. So to conclude, we have a novel methodology that lets us make predictions for any river in Scotland on any day of the year, providing that we have an air temperature data set. Where similar data sets are available, this could be used in other countries, and the outputs give us important management tools that can be used to inform riparian tree planting. We're actively working in this area, and future work is creating climate change predictions for Scotland's rivers using the UK CP18 climate change projections, and this will let us update these prioritisation layers of where's hottest, where's going to change the most under climate change. We're also developing a simplified process-based model that will let us generate a planting potential tool where you can identify rivers that are the most shadable, so where you're going to get the biggest reductions in temperatures for planting at large spatial scales. If you're interested in any of this work, go to our web pages and we keep them up to date with all of our new outputs. We've got a wide variety of information that might be of interest, from the papers, which are largely available open access, and the Shiny apps and topic sheets. If you have any comments or queries, please get in touch with us on Twitter. You can use the UOB World Water Day hashtag or the SRTMN hashtag. You can contact us on the SRTMN email address or go to our web pages. Thank you very much for listening.